Hello friends, welcome to CS Tunes. Today we are going to learn about deterministic finite automata, abbreviated as DFA. Deterministic finite automata is made up of two terms, deterministic and finite. It is finite because in this there are finite number of states, and it is the best example of the finite automata. It is called deterministic because we can determine that what will be the next state if we provide a particular input. So as we can see in the definition, it is written that in DFA for each input symbol, one can determine the state to which the machine will move and hence called deterministic finite automata or finite automata. In simple terms, it is also known as finite automata. It has a finite number of states. So whenever we can determine that on a particular state, if we provide a input, then what will be our next state? That means we can determine the next state if we know the current state and we know what is the input provided to this particular state. That's why it is known as deterministic. And it is finite because it has countable number of states, that is finite. So it doesn't have infinite number of states. The formal definition of a DFA can be represented mathematically by using 5 tuples, and DFA is represented using capital M. So our DFA can be mathematically represented as M equal to capital Q, comma, summation, comma, delta, comma, Q naught, comma, F. So these are the 5 tuples that are used to represent our DFA. Now let's see the meaning of these 5 tuples. So the first tuple, capital Q, is a finite set of states. That means it tells us that what are the states involved in any particular machine. And since I have already told you that the states are countable, so they are finite. Summation is a finite set of input symbols. Now, the input which we are providing to a particular machine is also a finite set. That means we can count the input that can be provided to a machine. So that's why it is a finite set of input symbols, and it is also called as alphabet. So you can say either you can call it a summation or you can call it as alphabet. So it is a set of input symbols. Now delta is our transition function and it maps Q into summation tends to Q. So let's see what does this mean. Now it means that suppose we are on a particular state. So our state will be determined from the set of state that is capital Q, and we provide any input from the set summation. Then the next state to which our machine will move will be determined from the state capital Q only. So let's take an example. Let's say capital Q consists of two states. So capital Q is equal to, let's say there are two states, Q naught and Q1. So Q naught is our initial state and Q1 is our final state. So I am going to tell you what is initial and what is final. First, let's see what does this mapping mean. Now summation is the set of input symbols. So let's say our summation is equal to A, comma B. So that means we are providing two inputs in the form A and B. Now delta tells us that how we are going to move from one state to another state if a particular input is provided. So let's say for example we are on the state Q naught. So this is taken from the set capital Q. So we have taken the state Q naught from capital Q. Now let's take any of the input from the summation, that is set of input symbols. So let us consider a input symbol A. So suppose we are providing a input symbol A when we are currently on the state Q naught. So we have used the symbol from summation. That means we have provided an input symbol A from the set of input symbols, that is summation. Then we will move to some other state. Let's say we are moving to a final state, that is, in this case, let's say it's Q1. So we are moving to a state Q1. So that is also from the set of states, that is capital Q. So delta is a transition function which maps capital Q, that is our current state, into the input symbol that we are providing and the new state to which our machine will move. So we can say that this is our current state and this is the new state to which our machine is going to move. Now, if we talk about the transition function, that is delta, so it can be represented in the three ways. You can use either a state diagram. So this is a representation in the form of a state diagram. We can also use a table to represent delta. So in case we want to represent the same state diagram in the form of a table. So here the states will be there and then the input will be provided, and similarly let's say there are two inputs A and B. So from the state Q naught using a symbol A we are moving to state Q1. Suppose from the state Q1 using a symbol B we are moving to state Q1 only, then we will write over here Q naught, because when we are on the state Q naught and we are reading the input symbol B, then we are moving to the same state. There is a loop over the same state using the symbol B. So that's why we are writing a Q naught over here. So in the similar way, you will be also providing the details of the state Q1. So for Q1, what will be the movement to the new state when we are reading a input symbol A, and what is the movement to the next state when we are reading a input symbol B. Let's say for example there is a loop for A and B both on the state Q1. So what we are going to write for symbol A, the state will be Q1 because there is a loop on the state Q1 only, and for B also there is a loop on the state Q1. So this is the way in which we can represent the delta, that is our transition function, in the form of a table. Similarly, transition function can also be represented in form of a function. Now, in order to represent this diagram in form of the function, let's take our initial diagram that we have taken initially. So this was our initial diagram. Now, if we want to represent in form of a function, then we will write delta, that is the name of our function, and it will be provided two arguments. The first argument is our state, that is Q naught, and the second argument is the input that we are going to provide, that is A, and the output will be the new state on which our machine moves. So over here you can see that the delta transition function can also be represented in the form of a function, that is delta, which consists of two arguments. The function is taking two arguments, that is the current state and the input. Then it will tell you that what will be the next state of this particular machine. So now let's see what is Q naught, that is our initial state, and what is F, that is the final state. Now, if we talk about any machine, so a machine starts from a particular state. So the starting state of a machine is known as its initial state. So we can say in other words that initial state is our start state. So over here it is written initial state from where an input is processed. That means from where our machine starts functioning. And since it is one of the states, that's why it belongs to the set of states, that is capital Q. So initial state Q naught belongs to the set of states capital Q. Now F is our final state. So as the name suggests, final state means the state at which our machine is going to stop. The state at which our machine will not move further. So that particular state is our final state. For a single machine, we can have a single final state or we can have a set of final states. So there can be more than one final state. So capital F is represented as the subset or equal to capital Q because there can be a single final state or there can be more than one final state. Now let's take an example that what is a state, what are the inputs and why are we talking about this. Let's take a simple example of an washing machine. Suppose we are talking about a washing machine. So initially our washing machine is not in the working state. So initially it is idle. Now as the input we can provide it dirty clothes, we can provide detergent, we can provide it water. So whatever we provide as the input is known as our summation. The states in which our washing machine can exist is represented as capital Q. So our washing machine can be in the idle state, it can be in the washing state or it can be used as a dryer. So it can be in the drying state. So if we are taking capital Q as the set of states, so it will consist of three states for our washing machine. Now, three states are idle state, it's taking the dirty clothes and washing it. That means that it is in the washing state and it has washed the clothes. Now it is drying those clothes. That means it's in the drying state. Similarly, the inputs that can be provided to a washing machine at different states are detergent, dirty clothes and water. So to make it simple, we are taking simple inputs and simple states. Now, when we have used the concept of the initial state, so whenever our washing machine is idle, it is our initial state, that is our Q naught. When it has washed the clothes, it has dried out the clothes and the final output is obtained. That means we have reached to our final state. So a deterministic finite automata is nothing else but it is a automata. It is a automatic machine that is represented mathematically using 5 tuples. Among these 5 tuples, we have capital Q, summation, delta, Q naught, F. So I think that this gives you a brief idea that what exactly a deterministic finite automata is. Now, in the next video, we are going to see that how can we represent a deterministic finite automata using graphical representation. So in this video, I have already provided you a hint of the state diagram. In the next video, we are going to learn that what are the different states and what are the different representations that can be used to represent a DFA graphically. Till then, stay tuned with our channel CS Tudes. Please like and subscribe our video and our channel also. Thank you.